These are the notes for theoretical and experimental probability. Theoretical probability is how likely an event is to occur. Probability can be expressed as a percentage, a decimal, or a fraction. In order to find the theoretical probability of something occurring, you need to take the favorable outcomes and divide that by the total outcomes. And that'll give you your decimal answer for your probability. If you want to change that into a percentage, all you have to do is multiply by 100, and then you have your percentage. If you want to keep it as a fraction, just make sure you reduce your fraction to its simplest form. Experimental probability is the likelihood of an event occurring by actually performing an experiment or a trial. So first, let's look at flipping a coin and getting a heads. So we have two columns here. We have our theoretical and we have our experimental. So if we flip a coin one time, the theoretical probability of getting ahead, if we think about our formula, our favorable outcomes, which would be getting ahead, we have one chance of getting ahead out of a total of two total outcomes. We could get a heads or we could get a tails. So we have a 1 out of 2 chance. That would be a 0.5 chance, or that would be a 50% chance, depending how you look at it. Experimentally, I'm actually going to flip a coin right now. And I got a tails. So experimentally, I got a 0 heads out of 1 total flip. So you can see that they are not always the same. Sometimes they will be, but they do not have to be. Flipping a coin 10 times. So if I flip a coin 10 times, what is the theoretical probability of getting a heads? There's 5 different chances of getting the heads out of 10 times. Again, it's still 50%. And then experimentally, if we flipped a coin, I'm not going to do that right now, but if we were going to flip a coin, you would take however many heads you had. Let's just say there was 4 heads out of 10 total flips, and you would reduce that to 2 over 5. Let's look at a different event now. This is rolling a die with numbers 1 to 6. So it's just a normal dice that we're rolling. The probability of rolling a 2, theoretically, the favorable outcomes, there's only 1 2 on a dice out of a total of 6 numbers, 1, 2, 3, 4, 5, and 6. So the probability is 1 in 6. The probability of an even number, there are 3 even numbers on a dice, those being 2, 4, and 6. So 3 even numbers, again, out of a total of 6 total numbers. And you always want to reduce your fractions to simplest form, so that is 1/2. The probability of rolling a 3 or a 6. So a 3 or 6 wins this, so there's 2 opportunities there, the 3 and the 6, out of a total of 6 numbers again, and we'll reduce that to 1 over 3. A number less than 2. So we're not including the number 2, just less than 2. The only number less than 2 on a dice is the number 1. So there's only 1 opportunity out of 6. And the probability of a number less than 7. Numbers less than 7 would be our 6, 5, 4, 3, 2, and 1. So there are 6 out of 6, which equals 1. If we made that a percent, that would be 100%, because of course when you roll a dice, you have to get a number from 1 to 6. Okay? Experimentally, you could actually do this and find your experimental probability by actually performing the experiment. Then we have consider the event of picking a card from a deck of cards. So hopefully you know about a deck of cards. There are 52 total cards in a deck of cards. And then you have your aces, your 2 through 10s, your jack, queen, and king. And then you have 4 different suits, your hearts, diamonds, clubs, and spades. There's 13 of each of those. So it says probability of selecting a diamond. So there are 13 diamonds in a deck of cards out of 52 total cards. So if we reduce that fraction, we would get 1/4. Probability of picking a 5. There is a 5 of clubs, a 5 of spades, a 5 of clubs, and a 5 of diamonds, and a heart. I forget if I said the one thing twice. But either way, there are 4 5s. So there's 4 that we could pick out of a total of 52 cards. So if we reduce that, we get 1 out of 13. The probability of selecting a red card, so half of the deck is red and then half is black. So the probability of red card, there's 26 red cards out of 52 total cards, and we get 1/2. And lastly, the probability of a queen or a 7. So again, there's 4 of every card. So we have 4 queens and 4 7s. So a total of 8 cards there out of 52. And if we reduce that down, I believe we can divide by 4 there. So that becomes a 2, and that becomes a 13. So 2 out of 13 chance. And again, we could do this experimentally just to compare. Okay, this says consider a bag that contains 3 red chips, 2 blue chips, and 5 green chips. And then randomly we stick our hand in the bag and 1 chip is chosen at random. So what is the probability of choosing a blue chip? So remember, your denominator is always your possible numbers. So you want to add up your total first. So if we have 3 red, 2 blue, and 5 green, there are 10 total chips. So the probability of blue, choosing a blue, there are 2 blue chips in the whole bag out of 10 total chips. So we have a 1 in 5 chance, or a 20% chance. Probability of a red, there are 3 reds out of 10 total. Probability of selecting a green or a red. So we have 3 reds and 5 greens. So there's 8 chances of doing that out of 10, which is 4/5. Probability of red or a blue. We have 3 red and 2 blue. So that's 5 out of 10, which is 1/2. Probability of red, blue, or green. So that's all of them. So there's a 10 out of 10% chance, or 100% chance of choosing one of them. And then lastly, probability of yellow. Notice there are no yellows to be chosen. So there would be a 0 out of 10 chance of choosing yellow, or it's a 0% chance. It's impossible to choose a yellow chip from that. Okay, here we have the results of a survey of 100 randomly selected students at a 2,000 student high school. And it looks like what they're going to do after high school. So there's different categories there, and then the different number of respondents. So it says, suppose one student is chosen at random. What's the probability of take a year off before college? So that's what we're looking at here. So you just have to find where it says that. So take a year off before college. And it looks like there's 12 people that did that. And again, 100 people were chosen here. So 12 out of 100. So if we reduce that down, it's 3/25. Now the probability of a trade school or a community college. So we want to find that. So trade school or a community college. So if we add 24 and 15 there, we get 39, again, out of 100 people. It's about 39% chance there. The probability of not a 4-year college. So if we look at that, so not a 4-year college would be community college, take a year off, trade school, or no college. So we have all those different possibilities. So if we add those up, I believe we get 57 there out of 100. And lastly, the probability of no college or a year off before college. So no college or a year off. So it looks like there's 18 people for that out of 100. And that would reduce to 9/50. So that's how we do probability from a table like that. Okay, we have a spinner here, and it looks like we have numbers 1 through 8. We have 4 white numbers and then 4 black numbers. So the first one here says, what's the probability of an odd number? That should say or a black space. So the probability of an odd number, we have 1, 3, 5, and 7. So there's 4 odd numbers. And then the probability of a black space is all of the even numbers. So we have 4 of those as well. So there's 8 total favorable events divided by total numbers, which there are 8. So there's a 100% chance that I am spinning and landing on an odd number or a black space. The second one there says probability of a prime number or gray space. So our prime numbers would be our 1, our 2, our 3, our 5, and our 7. So there are 5 of those. And then a gray space, which we'll say is white here. There are 1, 2, 3, 4 of those. Now, what you'll notice here is that you need to check, do you have any prime numbers that are on a white space or on a gray space? Let's look over to the left here. Notice that the number 1 here is a prime number and it's on a gray space. The number 3 is a prime number and on a gray space. The number 5 is prime and on a gray space. And the number 7 is prime and on a gray space. They are called overlapping events. When we have an overlapping event, we have to subtract out the number of overlapping events we have. So here's how we'll do this. The number of prime numbers, there are 5 of them. And the number of gray spaces, we said there's 4. So we have 9 total spaces, and we have to subtract out the number of overlaps. So in this case, we have 1, 2, 3, 4 overlaps. Once you subtract out your overlapping events, that is your new numerator. So our final answer is we have 5 in 8 chance of doing a prime number or a gray space. Okay, the next one says probability of a multiple of 2 or a multiple of 3. So our multiples of 2 are 2, 4, 6, and 8. And our multiples of 3 are 3 and 6. So it looks like we have 6 total options there. Do we have anything that's overlapped? The only overlap that I see here is the number 6. That appears in both of those. So we have 1 overlapping event, so we have to subtract a 1 out of that. And when we do that, we get 5 out of 8 chance. Notice your denominator is still the total number of outcomes. Okay, and last, it says the probability of less than 3 or a gray space. So less than 3, we have 1 or 2. And then a gray space, again, it's a white space here, it looks like. But there are, it's 1, 3, 5, and 7. So we have 6 total favorable outcomes there. And overlap-wise, it looks like the number 1 is our only overlap. So it's only one event we're subtracting out. So again, here it looks like our answer is 5/8. That is just coincidence that those three have the same answer. Okay, next example. It says a driver collected data on how long it takes to drive to work. And then we have our time in minutes there. And then we have the number of trips. So it says find the following. So we want to find the probability that a trip lasts 25 minutes. So we're looking at the 25, which is right here. And it looks like the number of trips there is 8. Out of the total number of trips, so our denominator, we're just adding up 4, 8, and 2. So that looks like it's 14. And then when we reduce that, it's 4/7. The probability that a trip lasts 30 minutes. So looks like there's 2 trips that last 30 minutes out of a total of, again, 14 trips. And we get 1/7. The probability that a trip lasts more than 20 minutes. So if we're looking at more than 20, that would be 25 and 30 minutes. So we have 8 plus 2 there, so there are 10 trips that last that long out of 14. And we reduce that to 5/7. And lastly, for this one, it says probability that a trip lasts 25 minutes or less. So 25 minutes or less than that. So it looks like we have 8 plus 4. We have 12 of those out of 14. So 6/7. Okay, and our last example here. It says a small deck of cards has 4 kings, 3 queens, 2 jacks, and 1 ace. Eli chooses one card at random 75 times and records his result in the table below. Okay, so we have our king, queen, jack, and ace on the left, and then the number of times we chose each of them on the right. And again, this adds to 75 times, as stated up there. So it says, theoretically, how many times would you expect to draw an ace out of 200 draws? Okay, so this is theoretically, not how many he chose, but theoretically, what would you expect? So if we're thinking about an ace, total number of cards up here, we have 4 kings, 3 queens, 2 jacks, and an ace. That is 10 total cards. And I only have 1 ace to choose from. So the way I would do this, I have 1 ace out of 10. So I have a 1 in 10 chance. If I draw one time, if I do this experiment once, I would theoretically expect to draw 1 in 10. But since I'm doing it 200 times, I would multiply this by 200. And when I do this, I get 20 aces. That's theoretically. Notice I did not use the table to figure out the theoretical because the table is actually doing the experiment. The next question says, experimentally, how many times would you expect to draw an ace out of 200 draws? So now I have to look at my experiment. And when I look at my experiment, it looks like I drew an ace 12 times out of the 75. So out of the 75, if I divide that by 3, I get 4 out of 25. Then if I multiply this by my 200, I would get 32 aces. So I would expect more aces experimentally than I would theoretically. And again, those numbers can be different or they can be the same. So what you have to notice here and remember is however many times you're doing the draw, that's what you're multiplying your probability by. So if it said you're doing this 10,000 times, you would multiply it by 10,000.